So the particular analysis is to form an equation of speed and torque. We usually transform those concepts, right, to the equivalent circuit, right? So if you recall our fundamentals of electrical engineering session, the phenomena, right, or the physical phenomena are actually converted with certain approximation and assumption to a circuit network, right? So what you see in this particular slide is actually a network of induction motor, right? And this is called per phase equivalent circuit, right? So because the three-phase induction motor is identical in terms of phases, apart from their angle or magnitude of the applied voltage and their spatial distribution are at 120 degree, right? But otherwise all these three phases are identical, right? So we can draw the per phase equivalent circuit, and if we identify how much is the torque or how much is the mechanical output per phase, and if we multiply by 3 because the motor is three phase, we can calculate the total torque developed by the three phase induction motor. So this is called per phase equivalent circuit. How it has been derived, I'm not going to discuss it because this is not a detailed induction motor lecture. So what I'm going to explain you here is, this is a supply. This is per phase supply block. This particular components are called stator component, right? So stator is nothing but a three-phase winding like this, a coil, right? So this three-phase coil, each is going to have its resistance and inductance, right? So the primary winding, or we can say the stator winding resistance and inductance are given as R1 and X1 values here, right? And so the one notation stands for stator and two notation stands for rotor, right? So these are the stator parameters. This is stator current I1. Now this I1 is actually divided into two parts. One is the magnetizing current IM and the rotor current I2 dash, right? So here we can write the simple equation as I1 is the factorial addition of IM plus I2 dash, right? So now here this is per phase equivalent circuit of entire motor. So this is a stator part and this is a supply section. Here you can see the air gap and the magnetization, right? So this particular session is modeled as the behavior of the air gap, right? So there will be a minor air gap in few millimeters between stator and rotor. These two parameters represent the effect of that air gap. Now there are two parameters connected in parallel. So this is called magnetizing resistance and the magnetizing inductance, and current IM flows in this parallel path, right? So here you can see how does the current IM is going to flow back. This will be the direction where current IM flows to RM and XM in parallel, and then combined total current IM will exit from this particular wire. So here you can see that the magnetizing current does not flow or does not get reflected into the rotor side, and it is not at all useful in generating the torque, right? So but actually this current produces an effect in such a way that there is a magnetic field established. That is why it is called magnetization current. So now going to the rotor part, so this particular section of X2 dash, R2 dash and another fictitious variable resistance is known as the rotor parameters, right? So if I consider the per phase stator voltage to be even, now this particular E2 dash is going to be same because these two circuits are connected in parallel. So in case of parallel connection, the voltages remain same. So the voltage V is applied, and according to this drop in R1 and X1, the remaining voltage is going to be appear across the rotor, and which is called E2 dash, and according to this voltage I2 dash current is going to flow through this parameters. Now what is the reason for this notation of making a dash over here? So if you refer to R2 or X2, right, these parameters are rotor parameters which are natural, right? But when we use the terminology called R2 dash or X2 dash, we are going to have this particular parameters referred to stator side, right? So R2 dash and X2 dash are the parameters referred to stator side. What do I mean by refer to stator side? Because we want to connect them in parallel, so I need to transfer these parameters from rotor to stator, and there will be a stator to rotor turns ratio, right? Similar to the mechanical engineering, if you transfer one speed and torque from one end of the gearbox to another end, you will be considering the turns ratio or the gear teeth. Similarly, in electrical engineering, here you will be considering the turns ratio. So the number of stator turns and the number of rotor turns per phase per pole, right? So this turns ratio is considered, and those parameters are referred with the point of consideration as stator. So now this is going to be a complete circuit, right? We cannot connect this three parameters to the stator side unless and until we transfer them to the stator side. So we actually multiply by the turns ratio square. So stator to rotor turns ratio, right? So what is the turns ratio? Here you will have a multiple number of turns in a coil, right? And that is called a turn, right, on a winding. So this is a per phase equivalent circuit. Similarly, rotor is having its resistance, its inductive reactance X2, and the rotor behavior is also governed by a parameter called slip, right? So we are going to study about this particular parameter, what is small s over here. So this is a fictitious parameter and it is variable because it varies with reference to the value of slip. So if we do this analysis and if we apply Kirchhoff's voltage law to this particular circuit, and if we calculate the current flowing through this particular rotor circuit and the power developed by the rotor, right? So there will be an equation of the power developed by the rotor, which is nothing but E2 dash into I2 dash, right? So this is a power, or we can calculate, we can apply the Kirchhoff's voltage law in this particular loop and identify how much is the rotor power. So the rotor power will be having the rotor copper losses and the remaining power will be available to the shaft. So how do we do the shaft analysis? So this is called the equivalent circuit analysis, and the next step is the shaft connection, right? So what will be the speed and torque, right? So from this particular equivalent circuit, the next step is derivation of the speed and torque relation. So now we have understood what is an equivalent circuit and its analysis. Without going into much detail, let's move ahead with the fundamental calculation, right? So here I would like to show you the basic calculations and basic equations. So for induction motor, you have to understand terminologies related with speed. So I'm going to call omega n as the actual speed of the rotor, right? Or we can say the speed of the motor, right? So this is the actual speed. Another term which we are going to refer here is omega ms, and which is called synchronous speed. So this particular synchronous speed is based on the supply frequency, right, and number of poles of the motor, or ultimately the design of the motor, and this can be correlated as 120 times frequency in hertz divided by number of poles of the motor, right? So this is a fundamental equation of the synchronous speed. You will find that the induction motors which are of 50 Hertz, 4 pole, right? For example, if I consider 50 Hertz as standard frequency of the supply in Indian power systems, and 4 number of poles are there, so here it comes to be 1500 RPM, right? So this is going to be 1500 RPM for 4 pole 50 Hertz motor, right? Now probably you can prepare a table where you have number of poles and frequency and omega ms, right? So if I consider 50 Hertz throughout, right, for all different pole pairs, right, number of poles will be always an even value, right, because it is a pole pair. So this is for 2 poles. What will be the value? This is going to be the 3000 RPM, right? For 4 pole it is 1500, for 6 pole it is going to be different, right? So you can understand that if you have a higher number of poles with the same frequency, the motor speed is going to be reduced, right? So this is the fundamental understanding of the speed of induction motor. Now, as we have seen, the actual speed and synchronous speed are having a difference, right? And that particular difference in speed is denoted by a term known as a slip. So a slip is a term denoted by small s, which is equal to the difference of synchronous speed and the actual speed, right? So usually the motor runs below synchronous speed, and therefore for the positive difference we deduct actual speed from the synchronous speed. You must be remembering that in the animation we have seen that the rotor is lagging behind the stator synchronous speed, right? So the synchronous speed at 50 Hertz is higher than the actual rotor speed, right? And this slip is usually considered in terms of percentage, not the difference, and that is in terms of the percentage of the synchronous speed, right? So this is a fundamental equation of slip, and this is the meaning of the parameter slip over here, right? So here the slip s is equal to this particular supply frequency related stator MMF, and here also you have 1 minus s factor, right? So this slip now is understood, right? So this is the difference between synchronous speed and the actual speed as a percentage of synchronous speed. So now if I do this analysis and if I apply the Kirchhoff's voltage law and if I establish a typical equation of torque developed by a 3-phase motor, right? So per phase torque is calculated first and it is multiplied by 3 because it is a 3-phase motor, so it is multiplied by 3. Directly writing this equation in order to move ahead quickly with electric vehicle application. So I'm not going to derive this equation, we are going to understand this equation only. So this equation is written as 3 divided by omega ms, right, which is a synchronous speed times a factor which is dependent on the voltage. This is per phase voltage applied to the stator of the induction motor into a parameter called R2 dash divided by S. So this is the numerator of the torque speed equation, and the denominator is actually based on only parameters. So these parameters are resistance parameters kept together as a square. So R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square, right? So this is the torque in Newton meter, provided this equation this value is in radian per second, right? And this value is in ohms, right? And this is in per phase voltage, right? So remember, when you put this equation, you must consider which type of connection you are considering, right? So if I tell you that find out the speed torque equation for a 4-pole 50 hertz motor, so you can put here this omega ms value in terms of, these are omega ms in rpm. You have to convert it into radian per second here, and if you keep this value, and if I give you the voltage value, right? So let's say the 440 volt delta connected motor, right? So you have to change that voltage to the per phase volt and put it here, right? Because we are multiplying this with 3, we are considering here per phase equivalent parameters, and this voltage is also per phase. R2 dash, R1 and X1 and X2 dash are the equivalent circuit parameters. So if I implement this equation and if I vary this parameter called slip, right? How this parameter is going to now vary? Usually its range in motoring region of operation is going to be from 0 to 1, right? How this value is going to be from 0 to 1? When this value can become 0, actual speed is equivalent to synchronous speed, right? So then it is going to become 0. So slip 0 means motor is running at synchronous speed. Slip 1 is the meaning that the motor is at standstill, right? So the motor is at standstill for slip value equal to 1. Now here, if I vary from 0 to 1 and if I plot the torque as a function of slip, keeping all these parameters constant, I'm going to get a relation between speed and torque, right? So now I'm going to move to the MATLAB window. I have a MATLAB program which implements this particular equation in terms of a MATLAB code, and we are going to plot the characteristic and see how actually the characteristics look like, right? Before going ahead with the MATLAB window, let me tell you that these parameters are motor design parameters, right? Or based on the motor construction and its design related parameters. So these values are experimentally derived, right? So these values are experimentally derived. Sometimes this may be given by the manufacturer, or if you have a motor and if you do the no load and the block rotor test on this particular motor, you can derive these parameters. What is a no load and block rotor test? So no load and block rotor test are nothing but you connect nothing on the motor shaft and you observe the power, and you can calculate some of the parameters from this, and if you do the block rotor analysis, actually you calculate those parameters, right? What is a block rotor test? You apply a reduced voltage, right? The voltage to an extent such that the rated current flows under the block rotor situation, right? So if you perform this particular experiment, you have to hold the rotor and you have to apply the enough amount of brake such that the rotor doesn't rotate at all. Under this condition, some voltages is applied, the voltage being equal to the amount of current which flows, which is called rated current. So let's say 10 to 20% of the rated voltage is applied, which is sufficient to flow the rated current under the block rotor condition. So the rated current flows under this situation and we are not getting any mechanical output. What will be the, yes, there will be a braking torque present, but what is the speed of the motor? It is 0 because this is block rotor condition. So speed is 0, torque is some value. If you multiply these two, the power is 0. But the input power is not 0, right? You are applying some voltage and the motor is taking some current and the motor is actually making losses, right? So if you do this loss calculation of no load and block rotor condition, you can calculate this all 4 parameters, right? So now I assume that some typical parameters from this test are known to you and we are going to enter those parameters in the MATLAB code.